Specialization is one of the most important techniques that LuaJIT and RaptorJIT use to make Lua programs run really fast like C programs. Now, Lua is a really high-level dynamic language, of course, and pretty much every aspect of a program's execution can be hooked and overridden at runtime, and so very little is kind of certain, at least compared with a C program, where the types of all the variables and the definitions of a lot of the functions and all of these kind of things are known ahead of time. So, specialization is the trick that the compiler uses to, on the one hand, optimize code really aggressively and do a lot of the same optimizations that a C compiler would do, and on the other hand, still preserve the full dynamic semantics of the Lua language. So to specialize a program, what you do is actually make a prediction about how things will be at runtime. So you might predict the type of a variable or predict the type of an object in memory, and then generate specialized machine code that assumes this prediction is true and can be really tightly optimized, and then this gives you a kind of a fast path of machine code that you can then branch to so long as you check that the prediction really is true beforehand. So what the compiler does is generate these blocks of very specialized and optimized machine code, and then branch to them whenever it can, and whenever it cannot branch them, it falls back on another block of code or a slow path or something like that. Now in reality, the JIT compiler specializes and optimizes code completely automatically and transparently behind the scenes. So you might actually write a whole application without ever knowing how it's been compiled, and if you're satisfied with the performance, then that's completely fine too. But if you really want to do serious optimization on your programs and performance troubleshooting and to understand the information you get from diagnostic tools like profilers, then it's actually really important to have a solid mental model of the way the compiler operates so that you can make reasonable predictions and make sense of information. Now, to understand the complete picture of how the compiler does all of its optimizations and manages all of its code is kind of a big topic, so I don't want to go through the whole thing right now. I want to look at just one isolated part, which is to do a thought experiment where we would suppose that instead of the compiler learning things automatically, that we would explicitly tell the compiler what information we want it to use for specializing machine code, and then we can think about what optimizations it would do in that case. So we can think of this as a little bit of a stepping stone for understanding the full picture later. So now imagine that we're writing, for example, a checksum function, which is the kind of thing that's really easy to write efficiently in C. A checksum function is probably loading machine integers from memory, and it's probably doing machine arithmetic and bitwise operations on them in registers, and this all translates really naturally into machine instructions on most CPUs. But if you would run the same kind of code in Lua with an interpreter, you would do lots and lots of kind of dynamic dispatch, and you would probably lose about 10 or 100 times of performance because the general overhead of dispatching would completely dwarf the actual real work that's getting done. So let's think about what we could do to tell a Lua compiler how to safely and effectively optimize something like a checksum routine. And one of the most obvious things would be to just tell it the type of every local variable. So if the compiler knows, for example, that a local variable happens to hold a 64-bit integer, that's really good. It can do arithmetic and bitwise operations on that variable using single machine instructions. It can also put the whole value into that register without needing to have any space for type tags, because if the type is known, you don't need the tags. So this is really helpful for the compiler to know for each register what type of value is in that register. And moving beyond just type declarations, a really useful mechanism for giving actionable information to the compiler is actually an assertion. So if we assert a condition to the compiler, that's actually really useful, because if the assertion would fail, then we're going to get an exception, and execution would not continue. So the compiler knows that if execution does continue beyond the assertion, then the assertion must have been true, so anything that was in the assertion is fair game for optimization. So we can use this as a really general way to convey predictions to the compiler. So one thing that we can do is specialize not only on the type of a variable, but even on its specific value. Sometimes if you have a variable with a numeric value, it might be very useful to specialize on this being a power of 2, or being perfectly aligned with the size of a machine word or something like that. This can make your arithmetic and bitwise operations much more efficient, and let you omit whole instructions sometimes if you're doing modular arithmetic, this kind of thing, which is great. Another really useful kind of optimization is if we tell the compiler the specific memory layout of objects on the heap. So if the compiler knows that a specific object is, for example, an array of integers of a particular size, then it might only take one instruction to load and store from that array. It might also not need to do any type checks if it wants to use those values in their native format as well. So it's really helpful to be able to tell the compiler what objects look like in memory. Another extremely cool case is specializing on the definitions of functions. So if you, in principle in Lua, when you call a function, you're going to branch off to God knows where, and when the function returns, you have no idea what's happened. But if you would specialize on the function having a specific definition, then you can actually inline the whole contents of that function into its caller and compile everything in one place. And this means that the compiler has the complete picture of everything that's happening and doesn't even have to emit a function call instruction, doesn't even have to have a call and return. This is great, and that's actually how the compiler compiles pretty much every function call in the program. And the last example is control flow. If you have a function with non-trivial control flow, you have if then else's and that kind of thing, you can actually specialize for the outcome of those branches. Every time you see an if then else, you could specialize for the case where the then branch is taken or when the else clause is taken. And this means you can flatten out the control flow for the function into a completely linear sequence of instructions, which is really fast and easy and efficient to optimize. And this is also what the compiler actually does with pretty much every branch that it encounters in the program. So between all of those techniques, you can actually get a function like a checksum to compile really, really, really efficiently and end up giving the compiler everything it needs to generate the same code that a C compiler would. And it's something that works very well when the compiler is able to make good predictions, when those predictions have kind of actionable optimization value, and then when in practice those predictions usually come true at runtime. You're actually running on your fast path rather than falling back on a slow path. So that's the basic way that the compiler makes predictions and generates specialized machine code based on the assumption that these predictions hold true. And thanks for watching. We'll check out the other cases, how the predictions are generated and what happens when you have multiple copies of the same code and all of that kind of thing another time. Cool.